The Fundamental Theorem of Calculus. In this video, we present the Fundamental Theorem of Calculus, which is the central theorem of integral calculus. It connects integration and differentiation, enabling us to compute integrals using antiderivatives, rather than by taking limits of Riemann sums. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It's very important for the continuity of this channel. Before we get to this crucial theorem, however, let's examine another important theorem, the mean value theorem for integrals, which is needed to prove the fundamental theorem of calculus. We start defining the average value of a function f over a closed interval ab. We know from arithmetic that the average of any numbers is their sum divided by n. This is useful for discrete mathematics, but usually in mathematics we deal with continuous functions, else we cannot apply calculus. The function takes an infinite number of values in ab. So adding them and then dividing by infinite is not an option. So we are going to use the same reasoning about the average. But now we are going to use a definite integral to find the mean value of a function on the closed interval ab. We divide ab into n subintervals of equal width delta x. We now take some number c sub k from each of the n subintervals of width delta x and evaluate the function at each of the points c sub k. The average value of the function may then be approximated as follows. Following through with the algebra, we can represent the numerator by using sigma notation as follows. Since delta x is b minus a divided by n, we can write 1 divided by n is equal to delta x divided by b minus a, and the average value becomes. This last sum looks familiar. It's the Riemann sum. Then, to get the exact average value, take the limit as n goes to infinity. Thus, the average value of a function is given by. If f is integrable on AB, then its average value on AB, also called its mean value, is given by. This means that the average value of a function is the definite integral divided by the width of the interval. If we multiply both sides of this equation by b minus a, the left side becomes the area of a rectangle. We can interpret the result in another way. The average value of a function is the height of a rectangle that would cover the exact area under the curve. We state the mean value theorem for integrals mathematically with the help of the formula for the mean value of a function that we have just seen. Mean value theorem for integrals. If f of x is continuous on the interval ab, then there exists a number c in the interval ab such that the mean value theorem for integrals states that for a continuous function f, there is at least one point c inside the interval ab at which the value of the function will be equal to the average value of the function over that interval. Now let's prove this theorem. If f is continuous, we could take lowercase m and uppercase m to be the absolute minimum and maximum values of f in the interval ab, and the function f takes on any value between lowercase m and uppercase m, and we can rewrite the inequality. We can multiply the inequality by b minus a. This inequality says that the area under the graph of f is greater than the area of the rectangle with height lowercase m and less than the area of the rectangle with height uppercase m. We now write the area under the graph of f of x by using the definite integral. If we divide both sides of the inequality by b minus a, we obtain, since the integral times 1 over b minus a is a number between lowercase m and uppercase m, the intermediate value theorem states that a continuous function on a closed interval always assumes its average value at least once in the interval, and the proof is complete. Before we prove the fundamental theorem of calculus, I will show you two important properties of definite integrals. I will give a justification for these using purely geometric arguments. Look at the areas below. First, as you can see, the definite integral of f of x dx from a to b is equal to the definite integral of f of x dx from a to c plus the definite integral of f of x dx from c to b. This is called the additive property of definite integrals. Second, let b equals a. It seems obvious that when the interval starts and ends at the same place, the result is 0. That is, the definite integral is 0. So we obtain that the definite integral of f of x dx from a to c is the opposite of the definite integral of f of x dx from c to a. This is called the reversing the interval of definite integrals. In short, when we invert the limits of an integral, the value of the signs of the integrals changes. Fundamental Theorem of Calculus, Part 1. Suppose f of x is continuous on AB. If you define a function as the definite integral of another function, f of x, then the new function is an antiderivative of f of x. This part of the theorem not only establishes a relationship between integration and differentiation, but also guarantees that any integrable function has an antiderivative. This part of the theorem states that the process of integration and differentiation are inverses of one another as well. We now prove the first part of the theorem. Apply the definition of the derivative directly to the function f of x when x and h are in the interval ab. When we replace f of x plus h and f of x with their defining integrals, the numerator becomes. Using the properties above, we can rewrite the equation as follows. The expression in brackets is the average value of f from x to x plus h. We know from the mean value theorem for definite integrals that f of x takes on its average value at least once in the interval. And we can rewrite the equation again. Since c is between x and x plus h, as h approaches 0, x plus h approaches x, forcing c to approach x also, because c is trapped between x and x plus h. This means that f of c is equal to f of x, and the proof is complete. Fundamental Theorem of Calculus, Part 2. The part 2 states that the value of the definite integral of a function on AB is the difference of any antiderivative of the function evaluated at the upper limit of integration minus the same antiderivative evaluated at the lower limit of integration. The subscript and superscript to the right of the vertical line indicate the lower and upper limits of the integration. In short, the vertical line indicates the operation substitute and subtract that is needed to evaluate the definite integral. The key to the proof is in writing the difference in a convenient form. Consider the following partition of the interval AB. We can break up f of b minus f of a as a sum of changes over the intervals. By adding the subintervals and using sigma notation, we get, by the mean value theorem, we know that there exists a number c sub k in each subinterval such that, by Fundamental Theorem of Calculus, part 1, we know that, and we can write the subintervals using delta x. Then, substituting into the previous equation, we obtain that the constant f of b minus f of a is a Riemann sum of f on this interval ab. Taking the limit of both sides as n approaches infinity, we obtain, and the proof is complete. Let's solve some examples to make the theory clearer. First of all, the integration of 1 over x is performed in the normal way. The integration of 1 over x is given by the natural logarithm of absolute x. Second, we evaluate the antiderivative at the upper limit and the lower limit, and then the difference between these two results gives the value of the definite integral. We solved the second example the same way we solved the previous one. We first find an antiderivative of the integrand and then substitute the limits and subtract. To solve the third example, we must get rid of the absolute value because there is no antiderivative for an absolute value. The standard approach is using the graph and the definition of absolute value. Using the definition of an absolute value, let's separate the integral into two possible cases to break up the interval in integration into two subintervals that are easier. We now proceed as in the previous examples. The fourth example is an application of the average value of a function to a physics problem. Pay attention.